Nature has a preference, left-handed. The universe itself is biased, and we didn't know. For 50 years, the greatest minds in physics built theories on the assumption that nature treats left and right identically. They were wrong. When the truth came out in 1956, it was so shocking that some physicists refused to believe it. Others sat in stunned silence. The foundation shook. Here's what makes this so disturbing. You'd think the laws of physics shouldn't care about directions in space, right? Gravity doesn't pull harder to the east than to the west. Light doesn't travel faster upward than downward. So why would nature care about left versus right? It seems absurd. Yet deep inside the atomic nucleus, in the weakest of the fundamental forces, nature absolutely discriminates. Particles know the difference. And that means something is profoundly asymmetric at the heart of reality. But let me back up. To understand why this terrified physicist, you need to understand what we thought we knew. There's this idea called symmetry, and it's one of the most powerful concepts in all of physics. Symmetry means if you change something about your perspective, about how you look at a system, the physics stays the same. Rotate your experiment 90 degrees, physics doesn't change. Move it to another room, same laws apply. These symmetries aren't just convenient, they're fundamental. They tell us what's possible and what's forbidden. One of those symmetries was called parity. The idea is simple. Build your experiment, then build an exact mirror image of it. Flip left to right. Run both experiments. Parity symmetry says they should behave identically. The mirror world should follow the same laws as the real world. And for decades, every experiment confirmed this. Electromagnetic forces, gravity, the strong nuclear force, all perfectly symmetric. Left and right were equivalent. We were certain. Then two physicists, Li and Yang, looked at some puzzling data from particle decays. Something wasn't adding up. Particles were behaving strangely, doing things that seemed to violate the rules. And they asked a question that seemed almost stupid. What if parity isn't conserved? What if nature actually distinguishes left from right? Most physicists thought this was crazy. The prejudice was so strong that people dismissed the idea immediately. But Li and Yang were serious. They said, test it. So they did. A woman named Qin-Xiong Wu designed an experiment. She took cobalt, 60 atoms, radioactive nuclei that decay by emitting electrons. She cooled them down to near absolute zero and applied a magnetic field to align their spins, all pointing the same direction. Then she watched which way the electrons came out. And here's the key. If parity is conserved, electrons should come out equally in both directions along the spin axis. Up and down should be symmetric. They weren't. The electrons came out preferentially in one direction. The mirror image experiment would have electrons coming out the opposite way. Nature was doing something different in the mirror world than in the real world. Parity was violated. The news hit the physics community like a bomb. Wolfgang Pauli, one of the greatest physicists alive, had bet against it. When he heard the results, he said he was shocked that God was left-handed. Einstein would have been astonished. The universe cares about handedness. Now, why does this happen? What's going on inside that nucleus? The force responsible is called the weak force, and it's one of the four fundamental forces of nature. It's the force that makes certain particles decay, that powers the sun through nuclear fusion, that governs neutrinos. And the weak force has this strange property. It only interacts with left-handed particles, literally. Particles have a property called spin. They're like little spinning tops. You can define handedness by the direction of spin relative to motion. Imagine a particle moving forward while spinning. If the spin points the same way as the motion, like a right-handed screw turning clockwise as it goes in. We call it right-handed. If the spin point's opposite to the motion, it's left-handed. And here's the bizarre thing. The weak force only couples to left-handed particles. If you have an electron spinning right-handed, the weak force essentially ignores it. Only the left-handed version participates. Nature has built-in handedness at the most fundamental level. This is completely unlike the other forces. Electromagnetism doesn't care about handedness. Gravity doesn't care. The strong nuclear force doesn't care. But the weak force absolutely does. And this means that if you built a mirror universe where every left-handed particle became right-handed, the weak force would stop working the way it does here. Particles would decay differently. Nuclear reactions would proceed at different rates. The mirror world would genuinely be different. Let me give you a concrete example. Take a muon, which is like a heavy electron. When it decays through the weak force, it produces an electron and some neutrinos. Now, neutrinos are particularly strange. They only exist in a left-handed form. There are no right-handed neutrinos, at least not that we've ever detected. So when that muon decays, it has to produce a left-handed neutrino. Conservation of angular momentum means the electron has to come out spinning a particular way to balance things. The decay is asymmetric. If you watch this in a mirror, the spins all flip. But the weak force doesn't flip. It still only likes left-handed particles. So the mirror decay would require a right-handed neutrino, which doesn't exist. The mirror process can't happen the same way. The decay rate would be different. The angles would be different. You could tell you were in a mirror universe just by watching particles decay. That's what parity violation means in practice. Now here's what bothers people. Why? Why is the weak force left-handed? There's no deeper explanation we can give you. It's just how nature is. We can write down the equations, we can describe how it works, but we can't tell you why it had to be that way. It's one of those fundamental facts you have to accept, like the speed of light or the charge of an electron. Nature chose left-handed weak interactions, and that's the universe we live in. You might ask, does this affect anything in everyday life? After all, the weak force is weak. It's called weak for a reason. Most of the time, electromagnetic forces and strong nuclear forces dominate, and those are parity conserving. So in most situations, left and right really are equivalent. Chemistry doesn't care. Biology doesn't care, at least not because of the weak force. Your body's handedness comes from molecular chirality, which is a different thing entirely. The parity violation in the weak force is buried so deep in nuclear processes that it doesn't show up in ordinary matter. But there's one place it might matter, the early universe. Right after the Big Bang, when everything was incredibly hot and dense, all the forces were equally important. The weak force was just as strong as the others at those energies. And if the weak force violates parity, that could have had consequences for how matter and antimatter evolve. Some physicists think parity violation might be connected to why there's more matter than antimatter in the universe today, why we exist at all, instead of everything annihilating into pure energy. That's speculative, though. What's not speculative is the experimental fact. Parity is violated. And that means our intuitions about symmetry were incomplete. We thought nature respected all these beautiful symmetries, and it turns out some of them are broken. Not completely. The combined operation of parity plus charge conjugation plus time reversal seems to be conserved. But that's a more complicated story. The simple idea that left and right are equivalent is just wrong. This changes how you think about the universe. You realize that the laws of physics aren't as symmetric as they appear. There's hidden structure, hidden preferences built into the forces, and you wonder what else we're wrong about. What other symmetries might be approximate rather than exact? What other biases might nature have that we haven't detected yet? The discovery of parity violation opened the door to a whole new way of thinking about particle physics. It also teaches you something about how science works. For decades, parity conservation was an accepted principle. It was in the textbooks. It was used to make predictions. And it worked for all the forces we'd studied carefully. But then someone asked, have we actually tested this for the weak force? And the answer was no, not really. We'd assumed it was true because it was true for everything else. That assumption was wrong. You have to test everything. You can't just assume symmetry because it's beautiful or convenient. The story of parity violation is also a story about courage. Li and Yang had to be willing to question something everyone believed. Wu had to be willing to do a very difficult experiment that might show nothing. And the physics community had to be willing to accept results that contradicted deeply held beliefs. That's hard. People are emotionally attached to their theories, but the data was clear. Nature doesn't care what we believe. It does what it does. Now let's come back to the mirror for a moment. Not the bathroom mirror, but the conceptual mirror. The idea of reflecting the universe left to right. Before parity violation, we thought the mirror universe would be indistinguishable from ours. Same physics, same processes, same laws. Now we know that's false. In the mirror universe, the weak force would couple to right-handed particles instead of left-handed ones. Neutrinos would spin the opposite way. Particle decays would be reversed. Could you live in that mirror universe? Probably. Most of chemistry and biology wouldn't change. The electromagnetic forces that hold molecules together are parity conserving. Your cells would function fine. But deep in the nuclei of atoms, processes would be different. Radioactive decay rates might shift slightly. Nuclear fusion in stars might proceed a bit differently. The universe would be subtly wrong. Not broken, just different. And if you were a physicist in that mirror universe, you'd discover that the weak force couples to right-handed particles, and you'd think that was normal. This raises a strange question. Why left and not right? Is there any physical reason, or is it just an accident? As far as we know, it's arbitrary. The universe could have been built with right-handed weak interactions instead. Nothing would fundamentally break. But once you pick one, you're stuck with it. And we live in a left-handed universe. That's just how the dice fell when the universe was born, if you want to think about it that way. Though I should be careful, there might be deeper reasons we don't understand yet. Here's another way to think about it. Imagine you're trying to communicate with an alien civilization in another galaxy. You can send radio signals, but you can't send pictures or physical objects. How would you explain the difference between left and right? You can't just say left is the direction your heart is on, because they might have their hearts on the other side. You can't point, they can't see you. For a long time, physicists thought this was impossible. There's no absolute definition of left versus right, but now there is. You tell them, take some cobalt, 6-0, align the spins, watch which way the electrons come out preferentially during beta decay. That direction is left-handed. Or you say, neutrinos always spin left-handed relative to their motion. If you detect neutrinos, you can determine left versus right. Parity violation gives you an absolute reference frame for handedness. The universe itself defines left and right through the weak force. That's extraordinary. Let me ask you something. Does this feel uncomfortable? It should. Our intuition says the universe shouldn't have built-in directions. Space should be isotropic, the same in all directions. And mostly it is. There's no preferred up or down, no preferred north or south. But handedness is different. It's not about directions in space, it's about chirality, about the structure of the forces themselves. And one of those forces chose a side. That's a fact about reality you have to absorb. What does this tell us about nature? It tells us that symmetry is a guide, not a law. Symmetries help us build theories. They constrain what's possible. They make calculations easier. But nature isn't obligated to respect them. If a symmetry is useful, but not required, nature might break it. And when we find a broken symmetry, it's often telling us something important. In the case of parity, it told us the weak force is fundamentally different from the other forces. It has structure the others don't. It also tells us that our prejudices can be wrong. Physicists in the 1950s were so convinced that parity had to be conserved that they almost didn't test it. The idea seemed ridiculous. But nature doesn't care about our sense of elegance or our aesthetic preferences. It does what it does, and sometimes what it does is deeply strange, violating principles we thought were fundamental. That's humbling. It reminds you that the universe doesn't owe you an intuitive explanation. There's a deeper lesson here about the nature of physical law. Laws aren't arbitrary, but they're not inevitable either. The weak force could have been different. Parity could have been conserved. The universe we observe is one of many possible universes consistent with mathematics and logic. Some features are necessary. They follow from deeper principles. Others are contingent. They just happen to be true in our universe. Figuring out which is one of the great challenges of physics. And finally, there's this. Parity violation reminds us that the world is stranger than it seems. On the surface, nature looks symmetric. Left and right appear equivalent. Up and down are interchangeable. But dig deeper. Look at processes involving the weak force, and the symmetry breaks. There's hidden structure, and that makes you wonder what else is hidden. What other secrets are buried in the forces we haven't fully explored? What assumptions are we making now that future experiments will prove wrong? So the next time you look in a mirror and see your reflection, remember this. That mirror image isn't quite the same as you. Not because of where your hair is parted, but because deep in the nuclei of your atoms, particles are decaying in ways that depend on handedness. The weak force in your body is left-handed. In the mirror world, it would have to be right-handed, and that means the mirror universe, taken seriously, isn't the same as ours. Nature knows the difference, and now so do you. The universe has a handedness. It's left-handed, specifically, and for 50 years, we didn't know. That's the mirror paradox that terrified physicists. Not that mirrors flip things, but that nature itself is fundamentally asymmetric in a way we thought impossible. The reflection isn't equivalent. The universe chose a side, and that choice is written into the laws of physics, whether we find it comfortable or not.